better way. Expressing concentration of solution. What's the big deal? Well, I Googled what the big deal was, because you're really not so sure on several things, and this popped up a lot. People dying because of dosing errors. You convert from one set of units to the other, or you prepared the solution incorrectly because your calculations were wrong. One way or the other, when you're making solutions of medicines and things that people are going to consume, you want to make sure you do it right. Lewis, what's the difference between a solute and a solvent when we're talking about solutions? Yeah, you hear him? The solute is kind of what you're dumping into the solvent. Technically speaking, the one that you have the most of is the solvent. Because you could be mixing a solid with a solid or a liquid with a liquid. What is going on at the molecular level when sodium chloride dissolves in water? Let's take a look and see about this. Water. Okay. Now remember our sodium ions were little gray ones, right? Because the chloride anions are always larger. And you notice what's starting to happen here. All the water molecules are moving around, but water's tearing still apart. It looks like these little red spheres, like here's water, but what are the red spheres? What atom are those? Yeah, the oxygen on the water. They're all oriented towards which ion is this? The sodium chloride crystal. Was that the sodium or the chloride anion? That was the sodium, because it's a tiny one. Those anions are huge. So they're all oriented towards the sodium ion. Why? Erica, why? Is water a polar molecule? Yeah, it's bent, right? And which side of the water molecule is it partially negative? On the oxygen side, because O is really electronegative, closer to F. H, they're going to be a little partial positive. Not full, but they're still, it's polar, a little bit. So that's why all those oxygens in the water are oriented towards the sodium cation. If it keeps going here, maybe there it is. Now they're grabbing chloride, anion. Okay. So this process is called, Sochi, what? Hydration, right? I guess tearing the crystal apart would be dissolving, right? But what we're really picking on here, hydration, right? That's really hydration. Okay. From the animation, sketch what a hydrated sodium ion would look like. So, Grace, I've got this sodium ion, and I just want them to be spherical, fine. And I'm supposed to draw these water molecules around it with all the what stuck onto the sodium? Was it the hydrogens or the oxygen? Oxygen was negative. So since sodium is a cation, it has to be all the O's stuck to it. So you kind of just draw it like this. You have all the O's stuck to it, right? You draw in as many as you want, really. Okay. In fact, the bigger the charge, the more water molecules are going to be stuck on there. And that's one bad thing about the animation is that the water molecules just kept piling on. It's not just as many as that can fit around the sodium. No, they just keep piling on. And they call that the hydration radius. That's kind of in the book, and they talk about it. The chloride anion. Whoop. What changes, Jessica? If you're going to sketch a chloride anion being hydrated? Now what? Anybody help her? No, the hydrogens are stuck to it. Right, well, stuck there's not a bond, but they're just kind of attracted, right? Now you draw all the H's there. And then you can fit on there. Okay. What do you think, Crystal? Would Fe plus 2 or Fe plus 1 be more strongly hydrated in water? She's right. Why? You're going off. Wrong way. Oxygen is this hydration idea, right? So we're talking about Fe plus 2, so we replace the sodium ion with these iron cations. Which one has a bigger charge? The plus 2 does. So since there's a bigger positive charge, yeah, those O's are going to suck up to it even harder and faster. And more of them, right? The hydration radius will be huge. Much larger than Fe plus 1 because the charge is bigger. Okay? Saturated solution of sodium chloride. Sodium chloride in water is supposed to be saturated. Jose, what is saturated? Oh, that's good. Here he said, it's like dumping in a bunch of salt in here, right? He said not all of it mixes in, so some of it lays on the bottom forever, right? That would be a saturated solution. The water can't dissolve any more, right? Okay. How could you get it? Here's the question. How could you get it to dissolve more? Heat it up. Yeah, get the stuff to move faster. Good. Okay. So sodium chloride dissolving in water. Here's an animation of it. Now, it's supposed to be saturated, though. They're trying to show some hydrated ions. Right? The hydrogens are sticking up to the chloride anions. Water molecules are... You see how, I don't know if you missed it, but one sodium ion came flying in this way and got put on, or no, it got taken off, and this one just got put on. They're trying to show that this sodium chloride crystal is decomposing or dissolving at the same rate it's being reconstructed. So just because there's so many ions flying around in there. That would be saturated. You just can't dissolve anymore. So even though Jose said that, you remember that you have that salt laying on the bottom of the beaker, it won't dissolve, it's changing all the time. Right? Sodium chloride solid is dissolving, but it's getting put back. So it's not the same sodium chloride ions and atoms down there. They're not dynamic equilibrium. They're being dissolved and replaced at the same rate. Okay. So if we have what is the difference between a saturated and a supersaturated solution? Well, if a saturated solution can't hold anymore, how is this even possible? What is a supersaturated solution? That would just... Oh, he's on to something. It crystallizes back out of solution. It's a supersaturated solution. That's what's going to happen if you shake it up. Supersaturated solution is very, very unstable, right? It's what you guys said. To get more sodium chloride to dissolve, it's saturated. Get more dissolved, you do what? You heat it up. Well, then more dissolve. But what if you cool it back down? Nice and slowly, right? Don't shake it. Nothing like that. And then it's just sitting there. It's waiting. It's very, very unstable. All you do is just shake it a little bit, and then it's all going to recrystallize out of solution. It's holding way too much. Here's a movie of it. And what they did is they took this sodium acetate, dissolved as much as they heated it. Right? They didn't show you this part. They heated it. And they added even more. Got it to dissolve. Didn't let it cool down. And now what they're going to do is, instead of shaking it, they're just going to add a little tiny crystal. So they're going to perturb it to this supersaturated solution. You can't even see it drop, but it dropped right in there. Now it's all coming out of solution. That's an extreme case, but that's probably why it's in the movie. Now what they found is, if you want to make rain, it's not as easy as they thought. I mean, you have air. Okay, fine, we have air, right? Need some water. Fine, dump in some water. Need water vapor. It's there. There's equilibrium going on. You can't see the water vapor, but you just have to trust that it's there. And then they say you need some wind. So fine, we'll make some wind. I don't know if you can tell, but maybe a little bit of a cloud form, but not much. Getting precipitation, getting cloud making is much more complicated. You need this region of saturated air. And it really is there. Once we dumped in the water, it happened pretty quick. I mean, the water is in equilibrium with the vapor. So that's really not the problem. The wind really wasn't the problem. The problem was to get that water out of the air. It's supersaturated. You need that little crystal that they dropped. You need something for all the little water molecules to grab onto. You need hygroscopic nuclei. In that demo, they used a little crystal. Well, in this little demo, I'm not going to drop in a little crystal. That won't be enough. I'm going to add some smoke. We'll get this match going really good. Drop it in there. I don't know if you saw it, but a little tiny puff of smoke came up. There's my hygroscopic nuclei. And there's our cloud. So you need hygroscopic nuclei. Now that means inside every single raindrop, every single snowflake, every single droplet in the cloud is a hygroscopic nuclei. Is it smoke? What is it? I'll give you a hint. Good guess. But if it was dust, I mean, that means when you're breathing in, you've got to be getting rid of this stuff all the time after a while, right? Not dust, not smoke. I'll give you a hint. 3/4 of this planet is covered with this. What kind of water, though? Salt water. That salt water to dissolve, the sodium chloride, the salt, most of it probably just falls back down, but the wind picks up a lot of it. So pretty much inside every single snowflake, every single raindrop, tiny little droplet in the cloud is a little tiny, what crystal? Salt crystal. Yeah. Okay. So you're really not drinking pure water, are you? Okay. 4 ways to express concentration of a solution. So there's 4 of them up there. Molarity, molality. Notice, Daisy, molarity and molality, one has a big M, the other one has a little m. But that's not my question. Daisy, in every single one of these ways to express concentration, it's really an equation with how many variables? How many variables in every single equation up there? She counts 3. Do you agree? Every single equation up there has 3 variables? See them? Every single equation up there has 3 variables. This is the meat of what we're going to be talking about today, right here. Well, if you're given an equation with 3 variables, the question, no matter how complicated, has to give you, Erica, how many of these variables? So every single equation up here has 3 variables. So we're going to be doing all this homework, and someone's going to look really complicated. But in there somewhere, they have to give you how many of these variables. At least 2. If they don't give you 2, you can't solve it. You can't solve for the third. So you just got to look. That's step 1, is figure out which equation it is. Step 2, plug in the 2 things they gave you. It sounds a lot simpler than it is, but that's all we're going to do. Okay? So let's start with, so this is given on, those equations are given on all quizzes and exams and things. How would you prepare? Okay. I'm starting out with, I think, this is the most complicated question. How would you prepare? You can't just give an answer of 10 grams. Right? You have to describe how you would prepare it. Now, if you're going to prepare this solution, great. It's a solution. All these are solutions. What's the solute and what's the solvent in this solution? What's the solute and what's the solvent? Yeah. And what's the solvent? Do you hear? The Na2CO3 is the solute. What's the solvent? H2. How do you know it's H2O? Yeah, aqueous. That's their way of saying water, right? Okay. So how would you prepare? Pretty much, you have to imagine yourself. You have to add, you don't know, how many, we're going to calculate that, how many grams of what? And dump it in water? Na2CO3. You have to add, we're going to figure it out, that's why I left it blank, so many grams of Na2CO3, sodium carbonate, add that many grams to water. We get how many grams total? Until you get 250 grams of solution. Okay. I guess you could also answer the question by saying, add, we'll figure it out, grams of sodium carbonate to, you could say the number of grams of water. Just subtract this guy from 250. That works too. Okay. But that's what I'm saying. This question is a little more complicated because it says, how would you prepare? Okay. See how we're going to calculate it. Crystal, remember the game. We got to pick the equation. Top right over here. Mass percent of solute. Everybody agree? Yeah. 10%. Here's a big hint, I think, once they say the percent. Okay. Mass percent of solute. This one. So we are going to put in Jose, what numbers are you going to plug in here? 250 grams in the bottom here. Everybody, how about the 10? Where are you going to put that? Yeah, on the left side, the mass percent. Then up on top, we could just write mass of solute or mass of sodium carbonate. Either one works as long as you can write mass of solute, but then you have to remember, oh yeah, solute is sodium carbonate. Okay. I purposely left out the percent because otherwise I feel like pushing the stupid percent button on the calculator. So I left it out. Oh, did we forget something? Times 100. Okay, otherwise I feel like pushing it. I also left out the units because how I like to do these is if I need to or add some weird funky units, I do that outside of the equation. And I just put in the numbers because then it's so much easier to see what to do. We have to do a little research before we move on. Let's say we have B equals A over C or something, right? Valerie, the B is already solved for. But how would you solve for the A? A would equal what times what? Or A would be what? There's an easy way and a hard way to do this. I like doing this diagonal thing. Okay? So I want to solve, what did I say? A? I want to solve for A. So that means I got to get rid of the C. Has to go along the diagonal. So A would be B times C. Now you can also do it the long way. It's 2 steps, right? Okay, C's in the bottom, so multiply both sides by C, right? So the C's cancel, end up with C over there. But this is so much faster. And it works every single time. Just move things along the diagonal. I want to solve for A, so I just get BC is going to be A. What if I wanted to solve for C? Lewis, if I wanted to solve for C, do the diagonal game. Move the C to where the B is, right? Because if you're going to solve for C, it can't be in the bottom. So he's moving the C where the B is, and then you got to get rid of the B, move it to where the C was, right? So move the C up on the top, B down to the bottom, you end up with C over there, A is up here, B's down the bottom, right? Technically, you could write C over 1, but C, okay? So play the diagonal game. So play the diagonal game. The mass of sodium carbonate, Daisy, would be not in the answers. What would the numbers? What would all the numbers be? So I want to solve for just this guy. We got to get rid of him and get rid of him. So we have the 10. Keep going. Remember the diagonal. So the 250 goes up on the top or the bottom? The top. So we have 10 times 250. Got to get rid of this guy yet. Goes on the bottom, right? You recognized it? That the 100's up on top, so it goes on the bottom. 250's on the bottom, goes up there. So 10 times 250 all over 100. Okay. 10 times 250 divided by 100. About 25 is my answer. Oh. So that is what we put up here. Add 25 grams of sodium carbonate to water until we get 250 grams of solution. So we could say add 25 grams of sodium carbonate to how many grams of water? To 225. That would be another answer. Add 25 grams of sodium carbonate to 200. The total has to be 250. That also works. It seems to me this is easier, but they all work. Okay, do you see the game plan? Pick the equation, plug in the variables that you know. Now notice the difference in this question. It's not how would you prepare. So nice. Just one answer is all they give. In fact, it's how many grams of HBr. So that is our answer. Right? There's no how would you prepare stuff. So how many grams of HBr are in 25 mils of 0.18 big M, that's called molar, HBr? Erica, what equation are we going to mess with for this question? Molarity one. And I'm glad she didn't pick molality. She noticed that it was big M and not little m. Right. So it's the molarity. So we should write that down. Big M, molarity, moles of solute. And they called it total liters of solution. I think that's how we defined it up there. Yeah, total liters of solution. Sochi, how could I say she was right? Because I don't even see grams of HBr in the equation. Close. You're halfway there. Yeah, did you hear it? We're going to get the mole of solute. In fact, you could change the word solute, everybody, to, change it to HBr. It might look better, right? That helps to change it, right? So she's right. We're going to get the moles of HBr, then use, what is this called up here? Molar mass to convert it to grams of HBr. We'll have it. That's the big game plan. So what are we going to substitute in here, Grace? What are you going to plug in? Oh, she said you have to convert to 25 ml. Yeah, I have to convert it to what? Liters. All right, let's do that. 25 mils. Now, if you know the trick, you just move the decimal place how many places? 3. But if you don't know the trick, better actually work it out. 0.025 liters. I mean, divide by 1,000, you really just end up moving the decimal place 3 places. 0.025 liters. So where are we going to put the 0.025 liters, Jessica? On the bottom down there. 0.025. And how about some other numbers, Crystal? What else? Oh, Crystal. Jose, what other numbers can we plug in there? The what? 0.18. Where are you going to put that? Yeah, where that big M was. And up here, moles of HBr. So how are you going to solve for the moles of HBr, Valerie? What are you going to do? Yeah, she sees it. Good. She sees the diagonal. 0.18 times 0.025 would be the moles of HBr. Well, 4.5 times 10 to the negative 3. Or 0.0045 could be on your calculator. Either one's the same thing. So, Lewis, how do we get this into the right unit? The gram? Yeah, get the molar mass of it. 4.5 times 10 to the negative 3 moles HBr. Hydrogen is 1. Bromine is like 79.9. Yeah, thanks. 80.9. So in a mole, 80.9 grams. About 0.36. Oh, 0.36. Okay. Make sense? Okay. So the game plan for this really is you have all the equations, you just have to know how to use them. And realize every single time there's 2 variables that the question gave you, you just solve for the third. You might have to do some converting like you did in this question. Which of the following ions, Daisy, which of the following ions would you expect to have a greater energy of hydration? Magnesium ion or aluminum? Aluminum, because it's bigger charge, right? +3 is bigger than +2, so. Okay, let's try this one. Eric, what mass of solution containing 5% potassium iodide contains 258 mg's of Ki? What's that mg? Milligrams, right? Mg is milligrams, right? Okay. Sochi, what equation are we going to be using to figure this out? What's that? Yeah, the percentage one again. The mass percent of solute. All right. What was it? I got it right. I'll write it like they have it. Mass of solute over total mass of solution. Oh, what's the solute? Because I could write solute, but Ki, I might just put that in there. It might look better. All over total mass of solution. And don't forget the times 100 part. Okay. So Grace, what are we after in this question? What part of this equation, which variable are we trying to solve for? Mass of the Ki? Mass of solution? You agree? Yeah. Because the very first part is what mass of solution, blah, blah, blah. So they're after that total mass of solution part. This is what they want you to find, this guy. Let's solve for him. That means we have to know the other two. So the mass percent, everybody, is going to be 5. And then the mass of Ki? That's the question, right? Should we convert this 258 milligrams into grams? What if we don't? What would be the units of your answer if you didn't? Grams? Because if you have, this will be so many milligrams. If we didn't, if we just put it in there up there, right, this is, well, you can put the units in. This is a percent. This is 258 milligrams. And then we're going to solve for this one, total mass of solution. And then we have a times our 100. But our units will just come out in milligrams. So, what do they care what units you're in for mass of solution? They don't. So if they would have said what mass of solution in grams or in kilograms or in, but they didn't. So we can just leave it like this if you want. We can convert it to grams if you want, but there's no reason to because they didn't specify. Let's just leave it in milligrams. So if I want to solve for total mass of solution, Jessica, how would you do that? How would you solve for this thing? Okay, she's moving the 258 down here. Then she's moving the 100 down here. Now that, you see what, that's exactly right, but what do you end up with then? You end up with 1 over this. You see that? She's doing it right. She's doing the diagonal thing. She's doing it all right. Right? She's bringing the 258 down, the 100 down. But then you're left with 1 over your answer. So I wouldn't do it that way. Instead, do what? Move this up to where the 5 is, and move the 5 down there. Right? That's a lot easier. Right? You can do it the way Jessica was saying, but then you got to flip both sides in the end. Okay. So let's just move this to the top, because whatever you're solving for has to be up on top. So bring that up there and move 5 down there, and we'll have it. Total mass of solution. All right. We're going to bring it up where the 5 was, and move the 5 down. So the 5 has to go down. The 258 is still up there, and so was our 100. We didn't mess with it either. Oh, it's milligrams. We should write that in, otherwise we're going to forget. So 258 divided by 5 times 100 about 5160 milligrams, or 5.16 grams if you wanted to convert to grams. Okay. The last class didn't want to go to the board, so that's why I didn't ask you if you wanted to go either. That's why we're still sitting there. But go ahead and try this one. And I'll help you if you have some questions. Fructose is a sugar, right? They want to know how much water should be added to 1.75 grams of fructose to give 0.125 little n solution. So remember the game plan. Figure out the equation. Recognize they gave you two variables. You're solving for the third. Yeah. Yeah. I think it's hard to really recognize. You're right, the water's a solvent, but where would it actually tell you? So I think what you have to imagine is the difference between solute and solvent is the one that you have a lot more of is the solvent. So you have this stuff that makes sweet. So you're going to only have a little bit of it, and most of it's going to be water. I think that's how you're supposed to think of this stuff. So you're right, the fructose is going to be the solute, and the water is the solvent. But yeah, sometimes it's hard to see. So which equation are you using? Molality, the little m1, not the big m1. Hopefully you're using the little m1. Right? Yeah. 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 Do you see what you have to do with the 1.75 grams? Turn it into, hang on. Let's go back up a little bit. If you're using the molality equation, well, where'd it go? Here it is. Okay. How much water is what they're asking. What are going to be the units of your answer? They're talking about how much water you're going to add. It's going to be kilograms. You're going to be solving for this guy. And that's fine. 2 kilograms of water, or 0.9 kilograms of water, that's fine. That's going to be our final answer, kilograms of water. But like Jose found, or he saw, I can leave it here. I think it was 1.75 grams of fructose. It's not going to work. You have to convert it into moles. It says moles of fructose, not grams. You got to convert those grams of fructose into moles, then you can use the equation. No. Kilograms of solvent is just what you're going to solve for. So that would be when you solve for this in the end, that's going to be kilograms of water. But that solute, that fructose, you have to convert that into moles of fructose and put that number of moles up here. If you're not sure, ask. She writes faster than me, so I'm not picking on her. So Eric, about 9.7 times 10 to the negative 3 moles. Did you get that? Or 0.0097, something like that. So if you got about 9.7 to 10 to the negative 3 moles, I think you're on the right track for the fructose. Yes, you got to find out what the molar mass of this thing is. 6 carbons, 12 hydrogens, and 6 oxygens, and that number goes down there. If you got it, go on to the next one. What did you get as the final answer? 0.078? Did anybody else get about 0.078 kilograms of water as the final answer? Oh, you did? Okay. If you got about 0.078 kilograms of water, go on to the next one. That's the next one. Times 10 to the negative 3. Oh, I see what you're doing. Right, you got to convert it into kilograms, don't you? I see what Jessica's doing. She's taking these 45 grams on this one and converting it to kilograms. Yep. Because she recognized that as the solvent. Good. That's the first step in this guy. Convert those 45 grams of solvent into kilograms, because you're using the little m equation, and that requires kilograms of solvent. About 1 minute left. Yeah. Good. What you doing, Lewis? You got lost? How far did you get? You're on the caffeine one?
Well,
Okay, just go back to this one. Okay, little m. That's the 0.125. Yeah, because this has to be moles of solute, and they gave you 1.75 grams of solute. So first you got to recognize what's the solute and what's the solvent. Water. This is the solute. So, yeah, so this goes up on top, but it's in the wrong unit. It's in grams. So you have to write 1.75 grams of C6H12O6 and convert that to moles of C6H12O6. Yeah, and then you have to add up 6 carbons, 12 hydrogens, 6 oxygens. That number goes down there, and you have mole up on top. And then you stop, right? And then that number, whatever you get, goes right there. And then you're just going to solve for kilograms of water. You're done. If that goes up here, 0.125 goes down the bottom, you'll have it. So we're about out of time. The solutions are online, so check them out before you do the homework. Make sure you can do these in-class problems.